Hey everyone, welcome back to Take You Forward. We will be starting with a new pattern of DP, which is the partition DP. And this is kind of like a tough pattern. It's a tough pattern. It isn't as easy as the previous patterns where we have done 1D DP, we have done 2D DP, we have done DP on grids, DP on subsequences, and after doing all the problems on those patterns, you are pretty much comfortable. Similarly, I can guarantee you, once you have solved all the problems that I will do on partition DP, you will be very comfortable on partition DP. Generally, all the other creators have just solved MCM or probably the Boolean parenthesis problem and they would have stopped. But over here, I will be solving, I think, 4 or 5 or 6 problems on this particular partition DP so that this gets right into your head. Okay, so let's understand what's this partition DP all about. So generally, in all the problems where you'll be said to solve a problem in a particular way, remember this: solve a problem in a pattern. Now, what is the pattern? For an example, whenever you do mathematical calculations, right? So assume you have been given something like 1 plus 2 plus 3 into 5, right? But if you put it like this, then the answer is different. But if you put it like this, then the answer is different. Don't you agree? So whenever you will find questions similar to these, like if you solve a particular pattern, like in a particular way, you get some other answer, or you solve in some other particular way, you get some other answer. That's when you can relate that to partition DP. Remember this: whenever there are multiple ways to solve, and probably they will ask you to find the best possible way, that's when you relate the problem to partition DP. So generally, how will you solve a partition DP problem? So as of now, I did tell you some rules for the dynamic programming, but for partition DP, there will be a different set of rules. Let's understand. So generally, in all the problems, you will have an array. In almost all the problems, you will have an array. And as you saw, over here, you solve this portion at first, and then this portion. Or you can solve this portion at first, or this portion. So similarly, in partition DP problems, you'll be given an entire array, and you will have to solve it probably this portion at first and this portion, or probably it can be you have to solve this portion at first or this portion, or probably you will have to solve this portion at first and this portion. So you will have to try out given a entire array, and generally the starting point will be known as the I, and this will be the ending point. Okay, and the partitions can be this where you solve this and this. So, or the partition can be this where you can solve this and this, or the partition can be this where you can solve this and this. So there can be a lot of partitions. Partition K can be here, partition K can be here, partition K can be here, partition K can be here. It can be anywhere. So there can be multiple partitions, right? There can be a partition like this, there can be a partition like this, a partition can be like this, and so on, like something like this as well. So out of all these partitions, whichever will yield you the best answer, you have to tell us that. So generally, all the problems which are like in a pattern, that can be solved using partition DP. And you have to basically, I can say, whenever you try to partition it in this way, you have to solve this portion, which you can call from I to K. So this portion, if you solve it like this, this is nothing but f of I to K. And if you solve this, this is nothing but K plus 1 to J, right? So again, if you're trying a K here, this is I to K, and this is K plus 1 to J. So similar pattern of problems can be solved using partition DP. So I just gave you an idea about how to approach the problem. So in order to understand partition DP, the first problem that we will solve will be MCM. What is MCM? Matrix chain multiplication. Okay, so in order to understand this, let's first understand what is matrix multiplication. Okay, so assume I give you 3 different matrices A, B, C, and the first dimension is 10 cross 30, the second dimension is 30 cross 5, the third dimension is 5 cross 60. So if I ask you, there is a matrix of size 10 cross 30 and that's the A matrix. There is another matrix of B which is 30 cross 5. Can they be multiplied together is the question. Can they be multiplied together is the question, and the answer to that is yes, Trevor, they can definitely be multiplied. Why? Because if you have done maths in your school, you know, if this guy, if these guys are equal, if the column of the first matrix is equal to the row of the second matrix, then the multiplication is possible. And how many operations do you require? Yes, how many operations do you require in order to multiply this? That's very simple. You take this guy 10, you take the common guy 30, and you take the other guy 5. So the number of operations or the number of multiplications required in order to multiply both the matrices will be 10 cross 30 into 5, which is somewhere around 1500 operations, if I have done the calculations correctly. Yeah, I have done it correctly. Now, what is these operations now? If you know, if I am multiplying some matrix like this, how many operations we generally do? So this is nothing but a 2 cross 2, and this is nothing but 2 cross 1. So again, this is equal. So multiplication is possible. What will be the resultant? The resultant will be a matrix of this size 2, of this size 1. Correct? How many operations will you do? 2 cross common 2 cross 1, which is 4 operations. Why 4 operations? Because first you multiply 1 into 2 plus 2 into 3. So what do you do? 1 into 2 plus 2 into 3. Next you multiply 3 into 2 plus 1 into 3. So 3 into 2 plus 1 into 3. So how many operations did you do? 1, 2, 3, 4. So there are 4 multiplications that you did. So that's easy to find. You write the first guy, you write the common guy, and you write the other guy. So if you multiply them, you easily get the number of multiplications or operations in order to multiply them. So these are the basics that you need to know. So assume I give you these 3 matrices. Let's again try to write it. If I give you A, B, C, okay, and I ask you to multiply them. What is A? A is 10 cross 30, B is 30 cross 5, C is 5 cross 60. Now if I ask you to multiply them, what are the ways that you can multiply? Obviously there are a couple of ways. One is you say, Striver, I will be doing it A, B, C. Like first I'll multiply AB, then I'll multiply C. Okay, that makes sense. So if I do the multiplications this way, let's see what will be the number of operations. So if I'm multiplying AB, that's 10 cross 30 and B is 30 cross 5. So what will be the number of operations? What will be the number of operations? 10 cross 30 cross 5 will be the number of operations. Agreed? So what will AB give? What will AB give? AB will give a matrix of 10 cross 5 again, because this is 10 and this is 5. So AB is going to give you a 10 cross 5 matrix. What is C? Let's write about C. C is nothing but 5 cross 60. So once you have multiplied AB, it will be a 10 cross 5 matrix. Now C will be a 5 cross 60. What is the number of operations? 10 cross 5 cross 60. So if I try to sum it up, this will be 1500 plus 3000, which gives you 45,000 or something like this. I think 4500 rather. 4500. 4500. So I get 4500 operations, which is indeed massive. Yeah, that's indeed massive. So let's write down the operations. It's 4500 operations. So that's one of the ways. What will be the other way? I can just try, well, listen. First, why don't you multiply BC and then let's multiply the resultant with A. I'm like, okay, makes sense. What is B? B is 30 cross 5. What is C? C is 5 cross 60. Okay. So if I multiply these couple of guys, I will get the number of operations to be 30 cross 5 cross 60. Makes sense? And the resultant that I will get will be 30 cross 60 because this is common. So the resultant will be 30 cross 60. What is A? A is 10 cross 30. A is 10 cross 30. So can I say this? The number of operations required will be 10 cross 30 cross 60, which this will give you, the number of operations will be 9,000 for this and 18,000 for this, which will give you 27,000 operations. So which way of multiplying these three matrices? So which way of multiplying these three matrices was a better way? I can say if I multiply this way, I will take 27,000 multiplication operations. But if I multiply first AB and the resultant with C, then I'll just take 4,500 operations. Is there any other way? Obviously not. So what I figured out was the minimal operations required. Yes, the minimal operations required was 4,500. So I want you to print this. Basically, given the dimensions, given the matrix dimensions, given the n matrix dimensions, tell me the minimum cost to multiply them to a single one. So for an example, if I take four matrices A, B, C, D, what can be the different ways? I can be like, Strive, I can do something like this. I will like first multiply CD, the resultant with B, and then the resultant with A. That can be one of the ways. I can be like, Strive, first multiply AB, then multiply CD. So first get the resultant, and then multiply both of them. Or I can be like, Strive, why don't you do this? ABC, okay, makes sense. Then D. So it's something like first multiply BC, then the resultant with A, and then the entire resultant with D. So there's a lot of ways. In which you can multiply. So again, which kind of DP? I told you, partition DP. Whenever a problem can be solved in different patterns, because I saw if I was asked to multiply ABC, there's two ways in which I can, this or this. And when I was asked for ABCD, there can be multiple different ways. So whenever such a problem arises, you think of partition DP. Yes, you think of partition DP. So what is given to you? Let's understand what is given to you. You are given an array. Remember this. You are given an array. Okay. Now, the example that I took was of four matrices. Okay. So imagine if I give you an array of 10, 20, 30, 40, 50. Over here n is 5. Over here n is 5. So if n is 5, this array resembles the dimensions of n minus 1 matrix or matrices. Let me explain you. So if I ask you, what is the dimension of A? The dimension of A will be 10 cross 20. If I ask you, what's the dimension of B? It will be 20 cross 30. If I ask you the dimension of C, it will be 30 cross 40. If I ask you the dimension of D, it will be 40 cross 50. So basically, 10 cross 20, 20 cross 30, 30 cross 40, 50. So if I try to index them, so can I say for the first matrix, the dimension is A of 0 into A of 1. For the second matrix, the dimension is A of 1 into A of 2. For the third matrix, the dimension is A of 2 into A of 3. Thereby can I write for any given input, the ith matrix will have a dimension AI minus 1 into AI. Makes sense. Yeah, favorite, like makes sense. So I can say I have figured out this, that the dimensions are given in this way. For any ith matrix, the dimension is A of I minus 1 into A of I. Okay. So you will be given this dimensions. You know the number of matrices are 4. Tell me the minimum number of operations required in order to multiply these matrices. This is the simplest question. So I hope you have understood the question, right? So how do you solve this problem? Definitely the way is partition DP. Again, whenever there is a pattern of DP, you have certain rules. Yes, you have certain rules. Rule number 1: start with entire block. Remember this: start with entire block or array. What does this mean? Over here we have four guys. So you say the function, hey, take the 4 guys and give me the answer. Yeah, you say the function, take the 4 guys and give me the answer. Like, it will be something like this. Let me just explain. So if I'm writing A, B, C, D, so these are the 4 guys. You start with all the 4 guys and you're like, okay, hey, listen, how can I solve this? I can either go like A, B or C, D. I can either go like A and probably it's B, C, D. Or probably I can go like A, B, C or D. Correct? So what you're trying to say is, okay, I was solving this. Now what I'll do is, I'll try to break the problem down into smaller problems. How can be the smaller problems be? It can be A, B, C, D. Or it can be A, B, C, D. Or it can be A, B, C, D. So what I did was, I took the entire problem, broke it down into something smaller. I'll try to solve them. And whichever way gives me the minimal will be my answer. So you will always start with the entire portion. You'll always start with the entire portion. Remember this. And you can always mark them by ij, where I is the start point. Like over here, I will be this A and J will be the D. Over here, I will be this, J will be this, I will be this, J will be this. Over here, I is this, J is 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 this. Because this in itself is a problem that you're wanting to solve. This in itself is a problem that you're wanting to solve. So, I is the start point. J is the ending point. Remember this. Start point and the end point is given to you. Perfect. So, start with the block and array. Always represent them by ij. Always represent them by ij, where I is the start point and j is the end point. Rule number 1. Rule number 2. Try all partitions. Try all partitions. Very important. Try all partitions. And how do you figure out which partitions are possible? Let's see. Over here, a partition was here. Over here, partition was here. Over here, partition was here. Over here, like you cannot again solve the entire thing. So there are 3 partitions. One is here, the other one is the middle, and the other one is here. There are 3 partitions. So probably you can run a loop to try out all partitions. Probably yes. Like, so run a loop. I'll explain you the loop. Run a loop to try all partitions. Remember this. Run a loop to try all partitions. Okay, makes sense. Next, 3. Return the best possible 2 partitions. Best possible 2 partitions. What do you mean by 2 partitions? Let's understand this. 2 partition. 2 partition. 2 partition. Which 2 partition is the best? Which 2 partition is the best? You return it. So 3 steps. Start with the entire block. Try all partitions because you're going to try out every possible way to solve it. And return the best possible 2 partition. That's it. So you take the entire problem, break it down into smaller problems. Every possible smaller problem. And you try to solve it. And you return the best possible partition that was like the best possible sub problem that you could break into. That's the straight funda. Okay, so something we have understood, that we have to start with f of ij, right? That's for sure. Now, what was given to us? Like, we knew that we had A, B, C, D, but we cannot think in terms of A, B, C, D. You have to think in terms of the array. Let's understand. You have to think in terms of the array. And if you remember, the array was something like 10, 20, 30, 40, 50. Correct? And can I say this? A was nothing but 10 into 20. The second matrix was 20 into 30. The third matrix was 30 into 40. This matrix was 40 into 50. Can I say this? I can. Thereby, what I can say is, hey, listen, if I am starting with, I can say this A, I can say this B, I can say this D. Where? If I'm looking for A's size, it's this guy and the previous guy. If I'm looking for the B size, it's this guy and the previous guy. If I'm looking for the C size, it's this guy and the previous guy. Something to the formula that we decoded. Previous into current. Thereby you can say if I'm resembling A, B, C, D, because that is what I'm looking to solve. My I will start here, that's the starting point, because that's what A is. My J will be the ending point. My D will be the ending point rather. Thereby I can say the starting point is 1 and the ending point is n minus 1. Over here, can I say, please solve me 1, 0, 1, 2, 3, 4, 1, 4. Please solve me the matrix 1 to 4. In what way returns the minimum multiplications to multiply matrix 1 to matrix 4. Remember this. It is the minimum multiplications to multiply matrix 1 to matrix 4. So we have got our start point, which is 1 and which is n minus 1. So every time the problem will start over here with f of 1 comma n minus 1. In other problems, you have to determine in this way. Like over here, since A was meaning this guy, like this guy into this guy, thereby is I started here. In some other problems, I might start here, J might end here. You have to figure where does your entire block lies. Once you figure that out, it becomes very, very easy. So you have understood what f of ij means. It states this is the block, give me the minimum operations required. Perfect. First step done. What is the next step? To write the base case. So what am I solving? I'm having an entire set of matrix for which I'm asking minimum operations. What will happen to this ij? Let's look. Ij actually shrinks. Whenever you will do partition, they will shrink. They'll shrink. So initially this is this much. Then a shrink will happen. Then a shrink will happen. Then a shrink will happen. What is the minimum that you will go? Ask yourself. You'll be like, Trevor, the minimum that we will go is nothing but when it's a single array. So the base case is very simple. If I is equal to j, you're solving an entire block. You shrink it, and you have came down to a portion where it is just a single matrix. Then the number of operations, what are the number of operations? Ask yourself. It's 0. The number of operations required is 0. So we figured out the smallest base case. The smallest case is when we just have a single piece of matrix. And thereby I can say we can easily return 0 because the number of operations will be 0. Start with the entire block. Done. Base case has also been written. Wow. So let's talk about the second point. Try all partitions. So let's go back and take the same example. This is the example given where we have this as the starting point, this as the ending point. So if I just write A, B, C, D, that will make you make things easier. Can I say I can have something like this? I can do a multiplication like this where I again solve this portion. Or I can have something like this where I solve this and I solve this and then I just add them up. Or I can have something like this where I solve this and I solve this and I add them up. Like, yes, Trevor, that actually makes sense. So can I say, if I probably, if I run a loop k, because first partition is this, the second partition that I can do is this, the third way that I can try is this. So can I say, if I run a loop from I to j minus 1, if I run a loop from I to j minus 1, for the first time, can I say it will be something like the first partition will be I to k and the other partition will be k plus 1 to j. We need to understand why j minus 1. I'll explain you that. Let's understand this. Let's take this example and try to write the values. 0, 1, 2, 3. So where is k? K is trying to go from 0. Let's try to write down the indexes so that this gets better. So k is basically running from 1 to 3. So what am I saying? 1 to 1 and 2 to, what's j? J is 4. So basically the first time, whenever k is for the first time, whenever k is 1, what happens? I'm saying 1 is to 1, which means just this guy. 2 is to 4, which means this guy. Next step, when k is 2, I'm saying 1 is to 2 and 3 is to 4, which means 1 is to 2 and 3 is to 4. Or I can say, if k is 3, I'm saying 1 is to 3 and 4 is to 4. Does that make sense? I'm basically trying to have different partitions. I'm trying to have different partitions. Make sense? This can be one of the ways in which you can go from I to j minus 1. I hope you understood why did I go till j minus 1. Because if you go till here, then there will be no one on the right. Thereby it's very important you go till j minus 1 because the right guy is k plus 1. So if you go till j, then k plus 1 will not be valid. So it's very important. Please make sure you go till j minus 1. Or one of the other ways is, you can do the other way as well. You can say, Striver, I will do k equal to I plus 1 and j till j. I'm like, okay, if you do this, then the partition will be I to k minus 1 and k to j. That's it. If you're running the loop from here to here, which means 2 to 4, then let's see what happens. If I is 2, which is the initial case, then it will be like 1 comma k minus 1. So 1 comma 1 f of 2 comma 4. I is k. If k is 3, it will be 1 comma 2 3 comma 4. If k is 4, it is going to be 1 comma 3 f of 4 comma 4. It's the same way. Either you run till j minus 1, then you will do a partition from I to k and k plus 1 to j. Or if you run from I plus 1 to j, you're going to do a partition from I is to k minus 1 and k is to j. Both of the ways are correct. So what did I say? Do the partitions. And in order to do the partitions, I know very simple. What do I need to run? I need to run a loop. And you can run any loop. So I will prefer running it from I till j minus 1. So that's what I will prefer. So I'll run a loop from I to j minus 1. That is something which I will do. Okay. What's the next step? We have to figure out the number of steps. And after that, we have to probably return the minimal of all steps. So let's understand this because second point is kind of half done. Return the best possible to partition. Let's understand this. This will give me some answer. This will give me some answer. And what do I need to take? I need to take the best among them. So let's understand how much answer. Like if I do it f of 1 1, f of 2 4. how much answer does this basically gives me? So A was 10 cross 20, B was 20 cross 30, C was 30 cross 40, D was 40 cross 50, correct? So we had 4 matrices, and this was f of 1 comma 1. So 1 comma 1 means one block of A, which will be 10 cross 20. And can I say, if you're multiplying BCD, at the end of the day, what will be the resultant? What will be the resultant matrix? So if you can try multiplying, it will be like B is this, C is this, D is 40 cross 50. So this is nothing but A. But if you multiply something as BCD, what's the resultant matrix? So assume you multiply this, you get 20 cross 40. Assume you multiply this, you get 20 cross 50. That's what you get. Even if you do it the other way, which is 20 cross 30, C is 30 cross 40, D is 40 cross 50. Even if you do it the other way, it's 30 cross 50, 20 cross 30, and if you again do it, it's 20 cross 50. No matter in which way you do the multiplication, the resultant matrix will be of size 20 cross 30 only. So I can say 20 cross rather 50, my bad, 50. So that's the resultant size of BCD. So if A is this, BCD is this, what are the number of operations that you will be requiring in order to multiply A and BCD? Because A was a part, BCD was a part. In order to multiply them, can I say the number of operations will be 10 cross 20 cross 50? That will be the number of steps, right? So where is 10 actually? Can I say, if you remember well, 10, 20, 30, 40, 50, I was here, J was here, and K would be probably here for this case, right? Where is 10? Let's see, where is 10? Can I say, whenever you try to multiply A and BCD, where is 10? 10 is right before I. So the number of steps required will be A of I minus 1 multiplied with, let's see. Let's come back. Where's 20? Can I say 20 would be here? You will be like, it's I. It's actually not I, it's K. Try taking some other partition, I'll show you that. It's actually K. So what you can do is, you can easily write array of K now. How's the other one? The last one is 50. Where's 50? At J. So the last one is array of J. So basically that signifies is, you had two parts. So when you combine them, the number of steps required will be this, right? Now you had two partitions. What are the two partitions? F of I K and F of K plus 1J, because BCD in itself will take some number of steps. BCD in itself will take some number of steps to get multiplied. So I can say, okay, the I comma K will take some steps. Let the function give me that, because I want the minimal number. Function will give me that. Or K plus 1 comma J will also, the left guy will take some steps, give me the minimal. The right guy will give some steps, give me the minimal. And these will be the steps if I do a partition on K. Right? And what I can say is, okay, I need the minimal of all. Probably I can store a mini equal to a bigger value, and I can say mini equal to minimal of mini comma steps, because I need the minimal among all. So this will make sure it gives me the minimal among all, and in this way I have pretty much solved the problem. Yes, we have. So every partition DP, remember, this is important. You will always have to do a partition, always. And after that, This was MCM, so you computed the number of steps. There might be some other problem. Steps, computations will be on the problem, but the left portion and the right portion will be solved by calling the recursion. Steps computation will depend on the problem. Like in MCM, we figured out this is what we are having. In some other problem, it might be something else that you have to figure out. So in order to understand the formula again, let's write the same thing: 10, 20, 30, 40, 50. Imagine I was here and I'm saying K is here and I'm saying J is here. Okay, imagine this is the starting point where I'm like, okay, divide them into AB and divide them into CD. Something we know for sure is this is 10 cross 20, this is 20 cross 30, this is 30 cross 40, this is 40 cross 50. And we definitely know this is going to give me 10 cross 30, this is definitely going to give me 30 cross 50, and when I multiply them, I'll get 10 cross 50 as the resultant. As the resultant, this is what I'll get, right? So can I say the number of steps, because at the end of the day, AB was 10 cross 30 and CD was 30 cross 50. So the number of steps, if you take CD and if you take AB, will be 10, 30 and 50. So again, you can relate. What's 10? I minus 1. What's 30? K. What's 50? A of J. So this is how the number of steps can be easily found. It's just before I, K and J. That's what the number of steps will be no matter how you multiply. And what you can do is you can solve this guy by calling the function, and you add this guy. So this will be the total number of steps taken, in short. Cool, I hope that makes absolute sense. So now what I'll do is I'll try to show you the recursion tree so that the working also gets clear, because that's very, very important. If you don't understand the working, it's going to be very messy. Let's understand the working as well. So what is the recursion tree? We started with A, B, C, D, or we were something like, okay, let's take 10, 20, 30, 40, 50, okay? And we were something like this is A, this is B, this is C, this is D, and this is our I, and this is our J. That's how the recursion started. This was the initial function call. Now, what kind of partitions you did? You did 3 kind of partitions over here. One partition you called was, you said, hey, listen, I know one thing for sure. I will myself take, if I do a partition something like this, if I just do a partition for 20, and I is he, J is Z, and this is the A. And the other one is 30, 40, 50, where I say this is B, this is CD, and I is this guy, and this is J. Basically what I did was I said just take A and just take B, C, D. So just take A and just take B, C, D. There can be 2 kind of partitions that I can do, right? So that's the first partition that you can do for K, where K will be initially over here. And this is what the partition will take place. Next time if you move K here, then it will be AB and CD. So you can again probably write, okay, it will be AB, which is something like 20, 30, and CD, which is nothing but 40, 50. It makes sense. And this time, this is I, and this is J, and this time, this is I, this is J. Or the other one can be K is here, thereby A, B, C, and D, if K is here. So what you can do is there can be another portion of type, which will be A, B, C, which is 20, 30, 40, and there's another thing D, which is 50. And this time, I is here, J is here, this time I is here, J is here. Perfect. Let's analyze. So we have, like whatever we have, this, whenever you run the K is here, it takes this guy, then K is here, takes this guy, then K is here, takes these guy. Out of all of these 3 partitions, whichever gives you the minimal, you're going to take that. Okay. So what's the first step that will run in the recursion? When K is here, this will get solved and it'll have some number of steps. So let's just solve this. You'll get a pretty decent idea, then you can solve this by yourself. So what will this guy return? It's a single matrix. Number of multiplications will be 0. Perfect. So I know one thing, A and BCD, they themselves will take 10 cross 20 cross 50, 10 cross 20 cross 50, because A and BCD themselves will get multiplied to take 10 cross 20 cross 50. And there was an F of this guy which gave you 0. And there's this another F guy which you have to figure out. Okay, so you have to solve this BCD now. You have to solve this BCD. So if I just take this BCD away again, and I write 30, 40, 50, and this is where the I and J stand. Now, how will the K work? K will be like, okay, once I can be here, and the other one I can be here. So there can be two possible ways. When I say I am B, and I can say I am CD. There can be other possible way where I'll say I am BC, and I am D. Perfect, makes sense. Now, can I say this? This time again, this guy will return 0. And there's CD. You have to solve CD. Basically, whenever you add this guy, this is returning 0. You have to solve CD. Again, it will go and solve C and D in two possible ways. I'll give you some possible answer. And you will eventually get the value, like which is the minimal of BCD. And that will come over here. And this will be added for this partition. Similarly, you'll get for this partition. Similarly for this partition. And you can easily get the minimal of this, this or this. And that is going to be your answer. Now, I could have done the recursion tree, but it will become very, very clumsy. Probably you can take pen and paper and try the recursion, but if you're good at recursion, you can visualize, right? So that's how you will do it. Let's quickly recap the entire thing because I know it has been a lot of information. Let's quickly recap it. This video is going to be long. So we started with partition DP, where I said you just have to decide in which ways you have to do, and you have to figure out the minimal. That's when you apply partition DP, and it's a tough part. So the problem that we solved was matrix chain multiplication, where we are given a matrix, n number of matrices, and we are being asked in what way will you multiply them? Like in which order will you multiply them? Like you can multiply AB at first or C, or you can multiply A and BC. So you have to multiply and you have to figure out the minimum number of operations, which of the pattern give. So I said, okay, I'm going to use partition DP. Why? Because there are different patterns in which we can do. And whenever that is, that's when we can apply partition DP. So we said that, okay, given in dimensions, tell me the minimum cost. So we were like, okay, fine. So we were given an array where we said that this is A, this is B, this is CD. And the size went on as A, I minus 1 into AI. Because if this is A, the size is 10, 20. If this is C, the size is 30, 40. Thereby, this is what the ith matrix size went on as. Now, I said I'll apply partition DP. So I said the rule is very simple. You solve the entire block. You solve the ij block. I'm like, okay. So over here, A was this, D was this. So this is the entire block. So you started from 1 and you went on till 4 rather. You went on till 4. So you just solved it like this. So I was like, okay, fine. You have understood that f of 1 to n minus 1 is what represents the entire block from A to D. So this means minimum multiplications to multiply matrix 1 to matrix 4. If this would have been f of 3, 4, minimum to multiply matrix 3 to matrix 4. As simple as that. Got it? So that's what I wrote as the first case. Start with the block. Next, base case. What about the base case? Base case is very simple. You know what is the smallest because you're taking the entire block to start off with. And whenever you're solving, if you're taking the entire block, it's the larger portion that you're starting from. So top, down, which is the lowest portion. It's going to be a single array element. So whenever it's a single matrix, if it's a single matrix, there is no multiplication required. Thereby 0 steps return. What is the next step? I said, I'm going to try out all partitions. And how can I try out all partitions? It was very simple. I said, okay, listen. One of the ways is I can go like this, like this. The other way is I can go like this, like this. The other way is I can go like this and like this. Okay. So I have to call for this guy and for this guy. So probably I can keep a k here and I can call ik. and k plus 1 to j. That's what I thought. Or probably I can keep a k here and I can call for kj and I can call for a of I k minus 1. Either I can call for these couple of guys or I can call for these couple of guys, depending on how am I looking to place k, because my main motive is to call these couple of guys. Doesn't matter if you call by this or by this. On that basis, we ran a loop from I to j minus 1 or from I plus 1 to j. Simple. So we ran a loop from I to j minus 1. And after that, we figured out that if there are two portions to be multiplied, then when they came across, the steps required will be this, and we got this formula. But this has to be solved. This is solved by calling f of ik, and the other portion has to be solved. So this is called by solving this. And this is the steps for one type of partition. There can be k type of partitions. Take all the steps and get the minimal of all the steps, and that's what you return. And in this way, you can easily, yes, I repeat, in this way, you can easily get this problem to be done. So without wasting any time, let's quickly code this up. So you're given the array and you're given the n. So you remember we need to write a function which basically is from 1 to n minus 1 and array, right? So let's quickly write the function from this. And we will have an f, we will have an int j, and we will have a vector of int and array, right? And I can say if it's a single size, we can definitely return 0. And what's the next step? You just do the partitions. So the partitions will be from I to k lesser than j and k plus plus. Basically till j minus 1 is what the partitions will be. You need the minimal, so probably you can keep the minimal mini equal to I9 or something like this. And you know the steps, you can easily compute the steps to be very simple. It's array of I minus 1 into array of k into array of j, and that's it. And once you've got this, solve the first portion, which is I to k comma array, and solve the other portion, which is f from k plus 1 till j till array. And whatever you get, if that is lesser than the previous partition steps, you basically replace mini equal to steps, and at the end of the day, you can easily return whatever mini you have computed, right? And what you can do is, let's quickly run this off and see if this is running fine. It does run, but it is giving time limit exceeded for certain cases. You have to apply memoization. What was memoization? Come on, guys. Let's come back to the iPad and check this out. Okay, so why did it give TL? Because we wrote a recursive solution, right? And what will the time complexity of this recursive solution? Let's understand. What will be the time complexity? If I go and try to analyze this, it will be somewhere near exponential. Yeah, it will be somewhere near very, very, very high, because you're going across every partition, right? And it will be tough to compute, so I'll just call it exponential. But if you want to take pen and paper, you can do it, but that's not required. So the time complexity goes as exponential. Obviously, this is something which will not work. How do you convert a recursion into something better? That's memoization. And I've already told, if overlapping subproblems exist, you can convert this into memoization. Let's see if it does exist. Let's see. So let's come back to the recursion tree. So you see a recursion tree. It is having BCD. Now when you solve BCD, you have a CD over here. Do you see? When you are trying to solve BCD, you are having a CD over here. And if you see over here, there's a CD. Do you see similar sub-patterns, similar function calls, f of CD, f of CD? So if you've computed this, can't you return this? You can. Thereby, I figured out that there are overlapping subproblems and I can apply memoization. In order to apply memoization, what is the first thing? See the changing variables. What is the state represented by? The state is represented by I and j. The state is represented by I and j. What is the value of I? The value of I is nothing but, at max, from 0 to n minus 1. So I can say n, this is n. So if you can have an n cross n dp, then you can easily store the answer of that state. Like for an example, this is CD, right? What is CD? Like if I ask you what is CD? CD is nothing but 0, 1, 2, 3, 4. So f of 3, 4. So you can say dp of 3, 4 is what you'll store. That's CD. That's CD. That is what you can easily do. So couple of steps and you can easily convert this into memoization any particular day. So what are the couple of steps? Just declare a vector dp n vector int dp, n minus 1. Once you have done this, just make sure you pass on the dp over here and right across here, just go vector int dp, the similar stuff, call the dp here, call the dp once here, and before returning dp of the state can store here, and has the state been previously visited. If it has not been previously visited, kindly return the value over here. Yeah, I think that should be fine. Yeah. So if you try to run this, this will be running and you will see that there is no further time limit exceeded because we have memoized all the states, right? If you can try submitting this. So guys, you see that it is partially accepted. Now, will this be accepted in an interview? Yeah, in interviews, if you tell this, the interviewers are like, okay, they don't force you to come across the tabulation stuff. But yeah, in IDs, it will probably give TLE. But again, the reason of setting the time limit strict is so that you go and learn the tabulation. Otherwise, people do not go and learn the tougher part. So I'll be telling you about tabulation in the next video because this video is already very, very long. But before that, let's discuss the time complexity of this particular method. So what we have done is memoization. So what is the time complexity? If like Strived is n into n states because I and j will have n and n states at maximum. But inside that, yes, inside the code, if you see, there's a loop running and there's a loop running, right? And you have to consider this because for every state, the loop will run. Every state you'll do multiple partitions. Thereby, for every time, like it's not exactly n times the loop runs, but you can say near about, it's a cube solution with a space complexity of bgo of n square as of now plus a stack space. Yes, there is definitely a stack space of bgo of n. This is the auxiliary stack space because if you go on the recursion depth, it's bgo of n. So that's what tabulation, that's what the memoization will be. In the next lecture, we will be doing the tabulation. So guys, if you have watched the video till now, I'm definitely sure that you have understood the partition DP. So just in case you did, please make sure you like this video. And if you're new to this channel, please do consider subscribing to us. And let me know in the comment section if you've understood this. With this, let's wrap up this video. Let's meet in the next one where we will be doing the tabulation format. Till then, bye-bye, take care.
Whenever your heart is broken